Hi guys, Saikran here. Today I am going to talk about one of my favorite topics in physics called cosmic inflation, and along with that I am going to discuss about bubble nucleation also. So in this video we are going to discuss about conventional Big Bang theory, quantum fields, bubble nucleation, mysterious dark energy, inflaton field, bubbled universes, multiverse, and a topic called eternal inflation. Inflation was proposed by one of my favorite theorists of all time, Alan Guth, master class. Alan Guth, you can listen to his lectures in MIT Open Courseware and everywhere. So it was proposed by Alan Guth in 1970s. Big Bang. So as the famous TV series Big Bang Theory opening goes, our whole universe was in a hot dense state 14 billion years ago. That was singularity. It was a very tiny dot with infinite mass. So it is a singularity, and from that our entire universe has formed. So as Stephen Hawking used to say, space and time both originated from Big Bang. So asking questions like where Big Bang happened and what was before Big Bang is meaningless, because Big Bang theory created space and time. So there was no before Big Bang and there was no point at which Big Bang occurred. What was there were some problems with conventional Big Bang theory. We have a so inflation solves most of those problems. So what is inflation? Inflation is the exponential growth spur of the universe at early stages. Inflationary epoch lasted for 10 power minus 35 seconds. In that very fraction of second, our universe expanded from the size of grain of sand to half of the observable universe in just 10 power minus 35 units time units. So this was it's compared to Planck time. So it is this was a exponential growth spur, and many physicists like to say inflation puts the bang in the Big Bang. So what are the problems solved by cosmic inflation? It solves mainly three problems called horizon problem, flatness problem, and magnetic monopoles problem. And along with that, it also explains the structure for formation of stars. The formation of stars is mainly due to quantum fluctuations at the early stage of the universe, which we are going to discuss in more detail. What is flatness problem? Our universe is too flat. Physicists measure this with a constant called omega. As you know, Einstein equation predicts that our space can have curvatures also, not just Euclidean space, it can be Riemann surface. So it can have any kind of curvatures, positive, negative, de Sitter spaces, anti-de Sitter spaces, but it is too flat for our liking. So what is the problem with that? Why do physicists are bothered by the fact that our universe is too flat? So consider we have a pen. I just place it on the ground and it just does not fall back, it does not fall to any direction. So it just stays there. How unlikely is that? How perfect you should be? So our universe is starting with the omega value of 1 is just as unlikely as that. It's just a metastable state being stable for a lot of time. So it's just unlikely. So inflation explains this problem, it solves this problem in a way. We are going to see how. And the horizon problem, as you know, after thousands of years after Big Bang, our universe released lot of energy in the form of photons, which now stays as cosmic microwave background. So there is a constant temperature everywhere in the universe of 3 Kelvin roughly. So it's like a white noise in the universe. So this is like a picture, thermal picture of the universe. This is called CMB, cosmic microwave background picture. So as you can see, almost uniform everywhere. Our universe has a constant uniform everywhere. There is no temperature gradient. So this was troubling many physicists. Why our universe is too uniform? It's uncanny. So why shouldn't it be? Why shouldn't our universe be too uniform? So consider when I take a hot cup of coffee and a cold cup of coffee, I just mix them and it forms an equilibrium mixture, right? So it takes some time to form an equilibrium mixture, because the hot regions and cold regions have to communicate, they have to exchange energy for this to happen. But at the early stages of the universe, our universe was expanding at a very fast rate that two points, 2 points had no time to communicate, because the space itself was expanding faster than light, and energy can be transferred at the speed of light only. So how does such a uniform CMB or uniform cosmic microwave background is observed? So this felt uncanny for many physicists, and this is labeled as horizon problem, and inflation solves this problem. Again we will discuss this ahead. And magnetic monopoles problem. So in classic electromagnetic fields, and we know that monopoles can't exist, but right now many physicists believe that magnetic monopoles can exist, and after string theory many believe that magnetic monopoles should exist. Magnetic monopole, as you know, electromagnetic field is also a quantum field. So in that quantum field, magnetic monopoles are nothing but twists in the quantum fields. So at early stages of the universe, the temperature was very high that magnetic monopoles should have been stable, and there should have been many magnetic monopoles, but we are not observing them yet. We couldn't observe even one. Why is this happening? We should expect after Big Bang, after quantum field theory, we expected that there would be many magnetic monopoles. So why aren't we observing them? Inflation explains this in a way, saying that the exponential growth spur diluted the number of magnetic monopoles. Again, let's discuss this later. Let's talk about many people's favorite topic, dark energy. Dark energy makes up 70% of our universe. Dark energy is the cause for accelerating expansion of the universe. What do I mean by expansion of the universe is accelerating? So even at the times of Newton, everyone know that our universe should have started from a very tiny region, and then it expanded into stars and cosmos and everything. It's like a stretched rubber band. After some time it slows down. It slows down due to gravity. Since gravity attracts, so all stars attract each other, and they should fall back. So it's like a stretched rubber band. It started expanding, and then it slows down, and after a point of time it should come back. But this is similar to if you throw an apple into there, due to gravity the apple slows down, and it stops at a point, and it falls back on the ground. This is what you expect with common sense. So this should even occur at universe scales also, cosmological scales also. But what our universe, what astronomers observed, mainly Edwin Hubble observed, was that our universe rate of expansion is not slowing down. It is not even constant. It is accelerating. So this was like a surprise. It is like throwing the apple into the air, and it is not stopping. It is just accelerating and going away into the space, even if you have thrown it at a very slight pace. So this was like a big surprise to many cosmologists, many physicists. So many people believe that dark energy is a reason for the accelerating expansion of the universe. So how can this happen? How can something accelerate a universe? So accelerating universe is nothing but the galaxies are pushed apart. The distances between galaxies is increasing faster than the speed of light itself. So it is like, in a way, gravity is acting repulsively. So can gravity act repulsively as per Newton? No. In Newtonian gravity always attracts, but we know that Einstein's gravity is the true gravity after general relativity, and in Einstein's gravity, gravity is the result of the curvature of space-time. So curvature of the space-time causes gravity. So from this equation, as you can see in the left hand side, the curvature of is the curvature of space-time, which is given by how much mass or pressure there in the universe. So left hand is a Riemann tensors, curvature tensors, and right side is a energy, momentum, pressure tensor. So if there is a negative pressure on the right hand side, this can lead to the curvature in such a way that 2 points in space move apart. It's like gravity is acting repulsively. So in Einsteinian point of view, gravity can also act repulsively. So if there is a constant negative pressure, this can happen. But what is negative pressure? Positive pressure is just pushing, right? Negative pressure is a suction. So what can result in such a negative pressure? As we know, every fundamental particle is made up of quantum, associated with a quantum field of its own. So even electron has an electron field, photon has an electromagnetic field, and the particles which we see in the standard model are excitations of this field. According to Heisenberg's uncertainty principle, the energy at any point of time, we can't be certain at quantum scales. So if you take at any point of time, you can't say that there is a constant energy. So as per Heisenberg's uncertainty principle, everywhere in space there should be a constant energy, constant non-zero energy, and this is called 0 point energy. So this 0 point energy doesn't decrease even if the space is expanding. So consider a certain energy, certain joules of energy in 1 meter square area, and if I increase that area, the energy density should decrease, but the energy density doesn't decrease here. Even if the space is expanding, the energy density remains constant. This can lead to a negative pressure, which can lead to a repulsive kind of gravity. So as we know, our universe is made up of Higgs field. Higgs field gives mass to fundamental particles like electrons and W bosons, Z bosons, everything. Higgs field is the reason for mass to the fundamental particles, and Higgs field also has a constant energy density. But that constant energy density is at a stable point right now. But there is a, as you know, energy tends to be at the least possible level, least possible energy scale. So every particle tries to achieve stability by giving out energy. It wants to be at the lowest possible level energy state. So here it is similar. Consider our Higgs field is at vacuum A, but it is stable because it can't go up on any direction, because as you can see from the picture, there are kind of hills, energy barriers. But there is a this is a false vacuum, but there is a true vacuum also. So there is another vacuum energy density to our Higgs field. So for our Higgs field to go to that point, it has to cross this barrier. So there needs to be some external push, but in quantum mechanics, as you know, there is a tool called quantum tunneling, in which the quantum particles can tunnel through the barrier, quantum tunnel through the barrier, and then it can reach to the local minima. So when this happens, energy is released because it is at vacuum A and now it went to vacuum B, and the resulting energy difference is released into space, which triggers the adjacent points, and that leads to a chain reaction in which a bubble of energy is formed, and it expands at an alarming rate, converting everything around it into the local minimum state. So it's like, let me give you an analogy. Consider our universe is filled up with a kind of a petrol or any other fuel. You know, as you know, in petrol and everything we have chemical bonds, and when you chemical bonds waiting for the energy to be released. When there is a tiny spark, it leads to a big fire. So you can say that our entire universe is like a petrol with a hidden energy, and a tiny spark can lead to releasing of this energy. This is called bubble nucleation. It can happen at any time. It's probabilistic. As you know, after quantum mechanics, everyone believes that our universe is probabilistic. So God does play dice with the universe. So vacuum decay. So if vacuum decays into a lower energy state, it can release an energy. So Stephen Hawking believes that vacuum decay is the way how we go, not with big crunch, not with heat death, and not with anything, but with vacuum decay is how our universe is going to end. Stephen Hawking used to believe. So why am I talking about bubble nucleation here? Because bubble nucleation, it means I want to say, energy in quantum fields, if there are many kinds of energy minima. So it can go from local energy minima to a true energy minima, and thus releasing an energy. Similar thing might have happened with inflation. There are two kinds of inflatory theories: old inflatory theories and new inflatory theories. Old inflatory theory was proposed by Alan Guth, in which there was a field called inflaton field, and its conjugate particle inflaton. It was in a stable state at a very high energy state, and then a quantum tunnel to that release of energy caused the growth spur, and the resulting energy is the reason why we observe all the matter particles with the resulting energy only. The matter particles, the electromagnetic particles, Higgs field, everything were formed. So from inflaton, decaying of inflaton resulted in the expansion of space, and we can see that the fundamental particles are formed. So this is kind of like a big bang. So but what is so this violates law of conservation of energy, right? No, this doesn't violate law of conservation of energy. How did universe come out of nothing? This is the greatest question man has ever asked. Out of nothing, how can a universe come, such a vast cosmos come out? So consider, again I am just saying this in a very dumbed down manner, but this is the essence of inflation. It's like considering our universe had a zero, it's zero, it had nothing, but you can write it as +1 and -1. So +1 energy is the matter we see around us, and -1 is stored in the curvature of space time. So total energy in the universe is zero everywhere. So zero, our universe has zero energy. So this is how the positive energy of matter is compensated by the negative energy of space time curvature. So but the old inflatory theory had a problem. In old inflatory theory, the inflation had to stop at some point, because we are not seeing the exponential growth spur at the similar to the inflatory epoch. Why aren't we seeing that exponential growth spur? So inflation had to stop at some point. So Alan Guth in his paper also mentioned that he didn't know when inflation stopped or why inflation stopped. But in new inflation theories, the inflation doesn't stop. It doesn't. In old inflatory theories, it goes from one point to another point, but in new inflatory theories, it just rolls down slowly, and that so when it rolls down slowly, energy is released, exponential growth is observed. So at and after that, in the region where inflation occurred, the energy density drops down, and it goes to a scale of dark energy we see right now. It doesn't expand that much, but in other places, at the boundaries, the domain walls, you can see it expanding very fast, normal inflation happening. So at a local region in space, the inflation doesn't occur, but at the boundaries it can occur. So inflation doesn't stop, it just carries on, resulting in many multiverses. So inflation just continues. It's just unlike in old inflation theories, it just doesn't drop to a lower scale, but it just slows down, rolls down slowly, and inflation just continues forever. So so we might be living in a multiverse. Our universe might be 10 to the power of 30 times bigger than what we observe. So this is what eternal inflation implicates. And bubbled universes. See how Big Bang is occurred. You can see that if you boil water, boil some water, you can see that there are many bubbles forming in between, and they collide and they result in some bigger bubbles, like result in some very tiny explosions or anything. You can see that in heating of water. Our universe kind of follows the same pattern. If inflation occurs at two different points, and these expansions or these bubbled universes, when they collide, results in a energy transfer, results in energy transfer into matter fields, and this appears as a Big Bang to that local universe. So inflation kind of explains why Big Bang occurs, and it also proposes that there are many bubbled universes. So inflation is truly a fascinating theory. And I said eternal inflation continues forever, and our universe is maybe far more bigger than expected. And so at the start we said that the problem solved by inflation was horizon problem, flatness problem, and magnetic monopoles problem. So how does inflation explain this? So inflation, since the universe which we see is very tiny bit of the entire universe, in that scale, even though our universe had an omega very much bigger or lesser than 1, but to a local minimum scale, our universe appears as if it has an omega equals to 1. So, our inflation solves this problem in a way that whatever parameters, cosmic parameters we are observing right now is just a local parameters and not global parameters. Consider a sheet of paper, it has many curves and many turns and twists, but if you take a tiny spot in that, tiny infinitesimal spot, you can see it is just constant over that region. So, our universe might be also in the same way. What we are seeing is a tiny part of what it actually is. So, inflation solves many problems and it opens up many new fields and opportunities into cosmology. So, it is one of truly one of greatest theories a human has ever proposed.